Peavey PVX P series powered subwoofer. Part of the ongoing equipment I'm working on, coming out of a PA system of our church. Stuff that broke, stuff that's needing to get repaired. Still got these speakers that I need to get worked on back here. This mixer power board and the subwoofer down here, which doesn't power on. Let's plug it into the dim bulb tester. Hey, it is plugged in. We might get a flicker of light when I turn it on, but that might be about it. Yeah, you see that? So nothing coming on down here. No power indication at the power LED. And all that does is kind of represent that we had some capacitors that were discharged and they charged up. But yeah, no worky. So what we'll do is I'll go ahead and take off this plate, unplug it from power source, and get it over on the bench.
The plate is easy to remove out the back of the subwoofer. We have a lot of dirt, dust. That's all going to get vacuumed out. But we have our power supply. It looks like it's rectifying to a couple different voltages. And then we hit this board right here, which is controlling our amplification, crossover, etc. All to output and feed to a speaker. Yeah, and I can already see one area of concern. Do y'all see it as well? Yeah. Whatever came up into here was a bit of high current or something, but we've got a definitive bad burn mark on this board. As a matter of fact, when we tried to power it up, the fan didn't even turn on, and we could see right here on the side, that is the pin connector for our fan. So whatever voltage is being developed right here from the power supply, we're not even developing a low voltage to feed this fan. That sits behind, looks like 2 voltage regulators down in here. Of course, one being these 3 pins right here. Okay, near this guy. Yeah, so the only thing I can really do at this point is I need to tear this down further and just start troubleshooting some components.
Well, before I tear it down further, I just wanted to make sure that I've got AC mains coming to that point, and I do.
Well, let's talk about what we're seeing here. A lot of burnt components all over the board, or at least burned up traces. That might be glue. That might not be a blown diode. I think that's just glue. So this is coming off of what, GP20B60PD, and we have another transistor on the other side, GP20B60PD. I have to look up these transistors here. That black one you see right down in there, power transistors most likely, and this one occupying this space right here. Anyhow, yeah, there's a lot of damage. It doesn't even look like really this guy is even making a connection at all. Nope, that has completely come off the board. So 4,750 ohm resistor, SMD resistor. Obviously the traces are all gone. All this is going to have to get cleaned up. So, and this is feeding up into, burnt up into even this side. So the glue down here, look, even that's cracked. So I got a lot of cleaning up to do. Probably trace repair. I'm willing to believe that these power transistors we have are probably they're probably cooked, need to be replaced. But there's just a lot of dirt as well. You see that? You see all this dirt right here. There's or dust buildup. All that's got to go. So I'm going to get this cleaned up and just start testing things. Come back to you if I find anything more significant than what I'm seeing right now. Let's talk about my findings for a minute. Obviously, this whole resistor network is going to have to be rebuilt. I'm going to rebuild. So these are testing around 20 to 25K roughly. I'm still going to end up rebuilding this resistor network up here. Even though these resistors read okay. I mean, the board is burned up. The traces will need to be replaced anyways if we're going to have any longevity to this this little network of resistors here. Obviously, these traces are all but gone. Well, some of them completely gone, some of them all but gone. Several of these resistors failed in a resistive measurement. Some measure good, but they're all going to get replaced anyways. Obviously, I will be rebuilding the circuit path, these traces all throughout here. Okay, this led me to looking at this little IC here, what you see marked Sierra 27952. That's actually short for IRS, or Indigo Romeo Sierra 27952. Is a half bridge converter control IC, and I suspect it is bad without powering up and actually being able to tell. I also believe, without pulling this out of the board, that this output transistor, this is actually a I think it's an N-channel MOSFET. What does it read there? GP20 Bravo 60 Papa Delta. Let me look that up for 1 second. So yeah, Online Sleuthing says that it is a from the IR International Rectifier Community. This is an N-channel MOSFET. Let's see, voltage 600 volts. Yeah, quite a few different characteristics. Not sure if we can get this one directly. Some of these we might have to find suitable subs. I assume I'll be able to get the MOSFET, although that's not always the case. This IC I might have to find a sub for. So what I'm going to do for now is I'm going to remove this IC from off the board and retest this diode just to see if it makes any difference. Well, where have I gotten to this point? Make sure to do a little diagram of the layout of all of our resistors and that IC, etc. These items I'm replacing along with the output channel MOSFETs. In this power supply, voltage regulator, whatever you want to call them. Okay. You may see that I've got copper pads put down here and conformal coating covering the carnage that appeared on the board there where the old traces kind of blew out of the way. So I've cleaned this off as much as I can with isopropyl alcohol. Then I scraped away at the PCB until I got some cleaner areas. I laid down this copper tape I have here, so I had to cut small strips. It's got an adhesive on the bottom side, so it's like a one-sided tape type copper thing. The upper side obviously being copper, a thin copper layer. These will become the traces between my pads, we'll say my surface mounted resistors as they go down. And as I solder those resistors in, I'll go back through with more conformal coating and cover up the areas of copper that's not used. So that's going to be my trace repair. Even though these resistors up here look bad and the board was burnt, there was no discontinuity in between the traces or pads pads there, so I just cleaned up the board as best as possible with removing as much loose carbon deposit using isopropyl alcohol and a cotton swab. And yeah, so that's where I'm at. It's now time to start rebuilding this section and all our components, and so that's what I'm going to do. While the conformal coating is drying there underneath my UV lamp, if for nothing else than posterity, I want to take a quick screenshot of this trace out right here. Of course, the upper resistors, one close to my index finger, those were all 30K. Then we had the IRS 27, what is that? 27952 half bridge converter, 4.75 K resistors and 5.62 K resistors in the orientation right there. Some of those resistors did not come with a silk screen on them. Okay. We also replaced GP20B60PD, which were, I had to find a substitute for them, and I think these are going to be okay, at least with the diode check that I did during the repair. Again, I haven't tested everything on this board. I've looked at a few surrounding capacitors, and they seem to be of okay value. I wasn't able to see a short unless I missed something. Okay, so there's that caveat. We repaired the board, replaced that IC because I did see an issue with it. And, you know, even with the diode check of the IGBTs out of this switch mode power supply, it's possible these older ones are fine, and that the failure did happen in that resistor array primarily. And we may have a working power supply, but just in case, you know, I give the caveat. We fixed damage, and we did find one bad IC. But that doesn't mean that we've actually fixed the problem. Those could always just be symptoms of whatever problem there was. Again, this thing was hit by lightning. It had to travel up and it went out somewhere. And I'm very surprised it didn't blow the fuse and it blew out that section of the board. Anyways, I'm waffling. The part number for the substitute of that in-channel IGBT is right there. You can see it. Got it off the Mauser. If it's focusing. There we go. So hopefully you were able to capture that. I'm going to hold on to these two old ones just in case if we have an issue with the subs that substitute parts that I put in. But I don't think we will. And I'm going to give this a little bit of time to cure. And when we come back, I'll have this, somewhat put together and we'll go and test it.
Okay, well, I've got it back together. I see the power LED is up there. It's like all my knobs are at the lowest setting. Got this in the on position. So hopefully no shorts. Let's turn this on and hopefully have no surprises. All right, there we go. Briefly on. Yeah, I think we're getting a tad bit of current draw. No power still. Nothing there. At least from what I can currently tell. Fan's not turning on. So it appears we still have more issues to figure out here. Yeah, so like I said, I think we fixed a symptom, but not the cause. We're still not developing lower voltages on the board. As you can see, that right resistor area, it does get hot again. But I'm more concerned with a spot that's over here. Now, ignore that. That's just reflections off of this post. You see these two, what are those? Those two diodes right there. Watch this when I turn it on. You see they're getting very hot. So we got to pull this power supply out and do some more troubleshooting.
Okay, I'm gonna use a speed through and an opportunity to say that I tested a lot. Things from optocouplers to ICs to capacitors, and I'm finding a component here and there that really doesn't make sense when I look at the circuit. Why we have some components that are out of spec, capacitors, somewhere near the switching of those actual in-channel MOSFETs. Several capacitors that are very leaky, got those replaced. Optocouplers that look like they're burned out at the output transistor output, got those replaced. And then eventually I run into an IC actually blowing up and replaced the in-channel MOSFETs that went out when that IC blew up, the driver blew up. And I'm like, okay, I replaced those, and then they blow up again, and they come to find out there's an SMD capacitor that's cracked, and I get that replaced, and now we're back to nothing blowing up, but the power supply is still not working. Here's the thing, these switch mode power supplies are sometimes very tricky. Everything from the frequency to the capacitors to the resistors. If just one thing is off, it's like they won't start up. Of course, there's a control circuit on one side. I'm actually going to talk about that here in a few minutes, but through this entire process that you're seeing, I have replaced components and tested and replaced components and tested, and still have not gotten this thing operational, which is kind of disheartening because I hardly ever run into things that are just beating me up this severely with trying to get fixed. But here you go. Here goes one that's throwing me for a loop. So for right now, just enjoy the music, and I'm I'm going to come back in with a discussion on the difference between a traditional linear power supply and, you know, what's used in most modern devices, a switch mode power supply.
Still working on this power supply for this Peavey. I was able to find some schematics. Let's talk about power supplies for a second. In a traditional linear power supply, from your line and neutral side, what you're most often going to have, and if I can break it down to simplest terms, is a big blocky transformer. That transformer is going to isolate you, provide isolation from the main supply, meaning your outlet. And then typically it's either going to step down or step up the voltage before rectification, such as what you have here in the switch mode power supply as well, a full wave bridge rectifier. Now you would have that transformer. Of course, we don't see one sitting here in the design of the switch mode. You would have a bridge rectifier or full wave bridge rectifier. That's going to take your AC, convert it to DC, and that is essentially your unregulated DC at that point. Now, from then on, in a traditional or linear power supply, you would have further rectification and voltage control to produce other DC voltages. Now, one item I didn't mention between that AC to unregulated DC to DC side is you'll also have filtering. Big old capacitors that are going to filter the AC hum coming in it, so you're not getting 60 hertz over your DC, and other filter and smoothing capacitors. Essentially, when you're after this rectifier, you don't have a, you have spikes, small inconsistencies in your DC direct current form. If you were waveform, if I could put it that way, looking on O-scope, you would need to smooth all those things out, and you would do that with capacitors. Okay, so that's traditional or linear power supplies. In a switch mode power supply, though, at least in this one, okay, I'm going to follow a primary what I would call primary or typical setup on how and of course there's going to be additional circuitry I won't discuss. This will be pretty atypical for a switch mode power supply. AC coming in. You may or may not have a transformer. Wouldn't be a big one, it'd be a small one, just providing isolation. You hit a full wave bridge rectifier, and you're not stepping down that AC at all before rectification, at least in this power supply. So you're going to have a pretty high DC, unregulated DC reference. We see over 300 volts there, and then this would be the negative rail. Okay, so we go from AC directly to an unregulated DC. Okay, and then that DC is fed into the bottom side of this, where we'll hit several resistors. It's going to step down that voltage. And then we start using it between here and this circuitry here to create a high frequency pulse width modulated signal. Okay, so we essentially take AC to unregulated DC back to a high frequency. It's going to look like a square wave or a rectangle wave, right? High frequency AC signal. So AC to unregulated DC back to AC, but it's high frequency because we use these small form factor transformers and switch mode power supplies to deal with high frequency. And of course, after we do that, that's stepping down or stepping up the voltage, barring what we need, the application. And then you see therein lies afterwards, we come back to DC regulation. And typically these are controlled DC voltages plus negative voltage rail or just a traditional voltage. Now, since we're on switch mode power supply and we go from AC to unregulated DC to pulse width modulated signal back, which is an AC signal, back to DC. We have to have some kind of feedback circuit, okay? And that's where this U14 that I mentioned previously comes into play. Now I've already replaced Q30 here, so if there's anything left that's causing, you know, something before this transformer to be bad, most likely it'll probably be this voltage regulator here. You don't really test it in circuit with a multimeter. You'd have to take it out, provide a ground to here, voltage reference point here, and measure the output. Okay, and you'd go off the diagram information for the component that you download. It's this data sheet, right? And then you can test it. But yeah, this will be your control, and essentially what we do, because this is a optocoupler here, this provides isolation as well between your primary half of the board and your secondary. Okay, so the ground over on this side should not be referenced to the ground on the primary side. You should not be able to use the ground on the primary side to measure voltages on the secondary. Okay, we're talking full isolation. So in the event you have that, it is most likely that if you're able to measure voltages across, or you have issues like that, you know, there's no isolation between the primary and secondary, it's probably going to be this optocoupler here, probably maybe this voltage regulator here. That's the issue. Of course, your capacitors and resistors, those could fail as well, but it's highly unlikely you see those fail, just as with like these diodes and everything. Again, everything I've replaced so far, minus the you know, some capacitors and stuff that were actually way out, and then that one optocoupler that was actually where was it? Was it this one? I think it was that one there. That one was bad. We've replaced a lot of different things, but it's mostly been one optocoupler. I've replaced this one as well. Maybe that was the one that was bad. Yeah. Replaced a handful of capacitors that were bad. We replaced the ICs, but we're still not getting what we need. So, you know, I've measured several of the capacitors. We've gotten them on order. I've actually just gotten them in. We'll replace them. But I think where I'll start is with U14, that voltage regulator you see right here. I'll get that into the power supply, and we'll see if that resolves the issue before I replace any other capacitors that may or may not be an issue. Again, most of those with the multimeter measured fine, but you know, they could still be leaky, and I don't have an ESR tester or anything along that line. All right, let me get that voltage regulator in, and we'll see how it does.
I wish I could say victory has been won, but unfortunately it has not at this point. More testing, more component replacements, and still not working. And I've had issues like this before, and it's always been like something small that I've overlooked. A resistor that measures good, but in circuit it's not making good continuity in circuit, and thus the device or whatever I was working on wouldn't power up. I've wasted a lot of money at this point trying to get this power supply to work, so now I need to make a concession in order to get this thing back in operation.
I don't really know how I'm going to edit all this video content together on this one, but I think I've exhausted every last thing I want to spend any more time on for this switch mode power supply right here. I mean, we replaced every capacitor, several electrolytic capacitor that is. I've replaced the full wave bridge rectifier, replaced several of these essentially optocouplers, several of the ICs, many diodes, several of the surface mounted capacitors, our in-channel MOSFETs, both resistor networks have been rebuilt. We've replaced these double diodes down at the bottom, you know, and a lot of this stuff wasn't testing bad on board, but a lot of it was too, especially in this section here in plot, you know, that being burned out. Also replaced these, you know, these capacitors in here with some, I believe they were Cornell doubler, you know, audio grade, non-polarized caps, you know, paper film capacitors, whatever. But you know, nothing has really restored this at this point. And you know, switch mode power supplies, they're really finicky, if I can be honest with you. You know, it could just be something I'm not seeing on the board. I've taken the multimeter to everything, and it could just be like, you know, there could just be in here like one resistor that's you know, even though my multimeter I'm seeing it's good, but it's just maybe the solder joint's not good, or maybe it's cracked, or once it's under power, or a capacitor or something like that. And without, you know, replacing everything on this board, that would just be a waste of my time at this point. And I've already pretty much wasted a lot of time. Plus, there are some things on the diagram that, you know, that are populated on this PCB that are not on the diagram. Like this whole section right here with these two diodes. Excuse me. Was that a transistor and a voltage regulator, or double diode right there? This diode, that resistor, and that optocoupler sitting there. They're not even on this schematic whatsoever. They're not a part of this control network through here. You just have that one right there. Yeah, they're not on here. That's all I can say. That those parts are not on this schematic. So instead, here's what I've done. I actually went out and sourced a 180 watt power supply. What was nominal for this? It's written somewhere on here. 160 watts down here at the bottom was the original power supply, switch mode power supply that went on to produce all the regulated voltages. This is a 180 watt switch mode power supply that's taking AC in and converting it to 12 volts. So I have AC coming to this terminal board you see with the strappings right there. You see labeled 1, 2, 3, 4, 5, 6, 7. The first two inputs are for your line and neutral. The third one is for the ground. However, the ground also comes to here on the board, which I have used a little ground strap to get it onto this little terminal post you see right here, which takes it to the ground of this chassis. And so the ground is complete from this point where the ground is on the board all the way down through to the plate itself. Okay, so from there, this 180 watt power supply produces 12 volts, like I mentioned. Okay, that 12 volt supply is I've replaced this 24 volt fan with a 12 volt fan, and then I inversed the fan so it can blow air out instead of in, because all this was covered in dust, and I think it's going to be better long term to blow the air out, especially given here's our heat sinks there, then there's one way back here. I need this to take internal temperatures and exit it versus just pumping in air inside of a cabinet that really has no exhaust ports in it for air to really circulate. So whatever air does come into this via the vents up here, and I think there's some down at the bottom. No, I'm mistaken. Up at the top, this is going to suck the air in. It's going to come across this way. And then jettison it out this way. At least that's what I believe it will do in theory. And with these heat sinks being where they are at, I think overall that's just going to be a better fit, having the air exhaust than having the air come in. Okay, so the 12 volt supply fans being provided 12 volts via the supply, also 12 volts into this second power supply I have over here. This is a DC to DC converter. So we have 12 volts coming in. And at the output, we have our plus or minus 39 volts and plus or minus 12. This will feed the 15 volt rail. This will feed the 39 volt rail, whatever. And it will work just fine. I think the only downside is, I mean, you need at least 112 amps continuous for this DC to DC converter that will feed our amplifier board. So we have more than enough headroom from this power supply in order to do that. I think the only downside is this can only supply up to 500 watts of power. And I think this Peavey is a 900 watt board, but I don't know, maybe with this more beefy power supply, maybe that won't be such a big deal. Besides, it's not like the amp's turned all the way up all the time. So, and to be honest, between this DC power supply, and that fan, I have spent just as much money as I did trying to repair that switch mode power supply. So at this point, this is the more financial better decision. And what I'll do is I'll put a picture or something or a link for where I got the parts. This one I got off eBay, this I got off of Amazon. And yeah, so the 15-volt rail, you'll actually see that I want to actually show this coming down to our circuit board right here, feeding into these 3 resistors right here. When you trace it out on the PV amplifier, you'll see that exactly where these rails come to, instead of soldering them to that rail there. However, the 39 plus or minus 39 I did take to that rail, so I put those instead to here because it just, you know, it was a point right there. It was easier to get to. Okay, from there I secured everything with screws where I could get them to fit. There's a screw over here holding the board. I've also used some Loctite super glue because I don't want any of these screws to back out at any point and for any of this to get loose, because it's not screwed to the board the way the old part was. You can see we have some open posts. These posts right here, and even this one's technically open, even though I've got a zip tie going to it. That one is actually holding the board in, but this side is zip tied. I might throw an additional zip tie in over here to kind of fix it to that board. But it is pretty sturdy. Okay, now I wouldn't carry this by these parts whatsoever, but all the screws do have some Loctite on them, so they will not back out. You'll see that I included a plastic washer underneath this screw right here, because as I was putting it into the board, you have a trace right here, and the head of the screw can touch this trace. Now the trace is not exposed. There is some conformal coating over a lot of these traces, but as vibrations occur, I'm more concerned about the screw eroding away at the conformal coating and potentially shorting out this trace, whatever's there, to the plate. So I don't want that to occur, so I put a plastic washer in between. But I think that pretty much covers it. So at this point, the only thing I can really do is power it up and see if it turns on. All right, so here we go. Let me turn on over here. And let's power this up for the 13th umpteenth billionth time. And all right, we make sure I got this fan the right way. Yeah, it's actually blowing this piece of paper out. Good. This board is powering up, so we've got progress. Now, I'm not going to jump for joy too much yet. I'm glad we have a power light there. Concerning that enable circuit for the power supply, it also hits sections of our amplifier. So I am slightly concerned that because this doesn't include that enable circuit, this power supply that I put in here, I am slightly concerned that the amplifier side won't allow amplification. And whatever is, I might have to take an O-scope to the enable pin to see what's there. I think it has to be taken to ground. I'm not too sure, but what I can do right now is I can get a tone into here and see if we have an output. And if we do, then I'm not going to fuss about that enable circuit. We're good to go at that point. So let me get an 80 hertz tone in here, and let's see what we're getting at the output. Yeah, and unfortunately I was right. No power, no amplified audio out to the speaker whatsoever. I just made sure that my input was good. So what I ended up doing was at P2, I looked for my high pass and low pass out on my preamp, which is this board right here, and then all the way down at the bottom. Let me get something, I'll point this out to y'all. So all the way down at the bottom, you got ground, and then that second pin will be the high pass, and then ground, then low pass. And I was able to see the 80 hertz signal here, but I lose it at the output of the actual amplifier down here. And so in turn, I went over to the power amplifier. I looked at this AC detect signal because I know that that comes in via the power pin. Where is that at? Somewhere on here. Power supply connect. Yes, right here. You can see AC connect right here via the center pin, pin P20, which is where you see that. I don't know if I can. You can kind of see what I've already done. This center pin on that plug down there, where the plug used to be. Went in and tapped the center pin to ground. And here's the reason why I did that. It's because over here you got this little symbol. It says it's on when it's low, mute when it's high, and I was seeing 3.2 volts DC on there. Yeah, I was seeing 3.2 volts DC on there with my multimeter. I even put it up to the O-scope, and I see like a little dirty DC voltage ripple type wave going high on this line the minute the thing is turned on, right around 3.2 volts or so. So then I went over to the power supply. I looked for my AC detect signal, and you find it up here near Q3. So that MOSFET, or excuse me, not MOSFET, everything wants to disappear on me. There we go. We'll just do it that way. This optocoupler sitting here, and you can see as the optocoupler is turned on, AC detect, it goes through this transistor and it's shunted to ground. So I took that pin initially through a like a low 100 ohm resistor to ground, and then I just ended up taking it to ground directly. And either one worked just fine. I was slightly concerned if I went direct to ground, that'd be too much current, and typically inside there's a little bit of resistance inside of these transistors. So but I ended up taking it direct to ground, and it seems to be working just fine. And we can tell because as I turn on the input of my amplifier, we now have amplified output at the speaker. So now I just need to get it inside its housing, and we can test it out with the actual Peavey speaker to see if everything works. But yay, we have a working amp again with a new power supply and DC to DC regulator. Well, just as a quick mock-up, I got that 80 hertz tone going to a spare speaker I have in the office. And if I change the frequency, let's see, frequency, let's step it up. Yeah. All right, let me go get it into the actual case for it. All right, yeah, here we go. Plugged in, powered on. Let me get some music going to it. Yeah, and we got bass. Bark.